Now, the final part of our core material involves looking at what we call electrolysis. And electrolysis is, as we say in the definition down below, it's the use of electricity to bring about chemical reactions. Now, I don't know whether you remember from your junior cert or not, but we talked about simple electricity. And we talked about how electrons might move from one metal to the other, and how then we could use a power supply to push electrons from one metal to another. Well, in that case, we're going to restrict ourselves to the latter scenario. We're going to be using electricity in order to bring about chemical reactions by pushing electrons from one place to another. And depending on that flow of electrons, that will dictate where electrons move from and where electrons move to. So it's important that we get the basics right before we begin any type of in-depth conversation on electrolysis. So let's take a look. First of all, the reason why we're studying this is because of its historical importance. I mean, electricity up to the time of Humphrey Davy and Michael Faraday was really restricted down to the phenomenon of lightning in the sky, and people were in shock and awe at the power of lightning. Humphrey Davy and Michael Faraday were able to bring that power from the sky into the lab, and they did this in London, in the chemistry lectures in London, where they were actually able to demonstrate the power of electricity before a live audience. And it was probably one of the most life-changing experiences that those people had when they were able to see what these two guys could do with electricity. It goes back also into Italy, into Galvani and those kind of people too, we'll talk about in a few moments. But these are the two main players. Electrolysis was used very, very widely by Davy, and we know this because Davy was the guy who used electricity to strip out elements that hadn't seen before. So, for example, sodium hadn't been seen until Davy electrolyzed salt water. And then he got his sodium and he got his chlorine gas. So thanks to Humphrey Davy and his electrolysis experiments as well, the number of elements on the periodic table went from a relatively small number, about 20-ish, 25, up to about 60 in a very, very short amount of time. Faraday then, who happened to be a student of Davy, took over. And Michael Faraday then used it so widely that the word electrolysis became part of the English vocabulary thanks to him. So a couple of things we need to just briefly go over, a couple of terms that I'm going to be using quite regularly during this particular section. Electrodes. Now again, if you can remember back to your junior cert science, the electrodes are the objects that are placed into the liquid, okay? One of them will be positive, one of them will be negative. And there are two types of electrodes. First of all, you can use electrodes that are active, and that means that as the chemical experiment, chemical reaction goes forward thanks to electricity, that the actual electrodes themselves become involved in the chemistry. So chemical reactions can occur not only on the electrodes, but with the electrodes. And if that's the case, they're called active. If the electrodes are involved in the chemistry and change because of the chemistry, they're active electrodes. Otherwise, they are inert. And what that simply means is that they strip electrons or they deliver electrons, but they themselves don't get involved in the chemical process. Okay, so two types of electrodes, active or inert. The electrodes themselves are called the anode and the cathode. Now, sometimes people think, how am I going to remember the anode and the cathode? I'll give you an easy way in a moment. But the anode is where substances lose electrons. And the cathode is where substances gain electrons. And the reason for that is because of the movement of electrons. So at the anode, if anything approaches the anode, the substance, when it touches the anode, will lose electrons to the anode. Whereas at the cathode, the opposite is the case. Any substance comes in contact with the cathode, they'll be gaining electrons, taking electrons from the cathode and changing their electronic configuration or their charge. The electrolyte is the liquid into which the anode and the cathode are placed. Now, normally the electrolyte has to contain ions, and in certain circumstances the electrolyte has to have the same ions as in one or both of the electrodes, and we'll talk more about that later on. So the electrolyte, just a general term, the electrolyte is the liquid that contains ions into which the anode and the cathode are placed. And finally then, what are ions? Ions are atoms that have lost or gained electrons. Okay, that's all you've got to remember. The reason why substances lose or gain electrons is in order to become like the nearest noble gas, to have the same electronic configuration as the nearest noble gas, because at the end of the day, stability is far more important in chemistry than neutrality. Okay, so once you've got those terms in your head, no harm to write them out maybe and make sure you understand them. Let's go over what the simple cell is. Now remember what I told you at the start. We're going to be using electricity to bring about chemical reactions. So the first thing we notice about the cell is that we have a look here, the anode and the cathode and the electrolyte. Okay, so this is how we bring about the chemistry by means of our simple cell. And as I said to you before, the easy way to remember this, if you're wondering how am I ever going to remember it, is A, C, E. Think of alphabetical order. From the anode to the cathode to the electrolyte. So if you're talking about what way do the electrons flow, electrons will always flow from the anode to the cathode and into the electrolyte. So they'll flow from the anode to the cathode and into the electrolyte. And I did tell you before, an awful lot of chemistry, in fact an awful lot of mathematics as well in terms of the procedures, follow alphabetical order. So in this case here, if you're wondering anode, cathode, electrolyte, how do I organize them? Put them into alphabetical order, and that is the journey of the electrons. From the anode to the cathode, and then into, if needs be, the electrolyte, or the substances that are in the electrolyte. That's where the chemistry is going to happen. So the chemistry will happen down here when the electrolyte meets the electrons on the cathode. A power supply is needed, because the power supply is like an electron pump. It dictates what way the electrons are going to flow. Now, sometimes if you take two metals that are different, say for example copper and zinc, and if you bring them together, if you were to put copper and zinc into a piece of lemon and touch it off your tongue, you'll get a flow of electrons. Okay, you'll feel that zap of a battery, because the metals are different and they have different powers of losing electrons. So therefore they feed electrons to each other. So when you put your tongue between them, you actually complete the circuit and the electrons will flow. That's a natural flow of electrons, okay? Whereas here, in relation to electrochemistry, we put in a battery to dictate what way the electrons will flow, because the battery pushes the electrons in one direction. And normally the symbol we have for a battery is this one. So we've got a long side followed by a short side. And again, people often wonder, well, what way do the electrons flow? How can I remember what way the electrons flow? Which one of these is linked to the anode? Which one is linked to the cathode? And I'm going to give you a very easy way to remember this. If you take the long and the short and you simply join them together with lines, watch what happens. So in other words, you join the top of the tall part to the top of the short part on the top, and then the bottom of the long one to the bottom of the short one. Watch what happens. You get an arrow. And that arrow will dictate what way the electrons are going to flow. So if that battery is dictating this way, well then this side will be the anode to the cathode. So therefore the long side of this symbol is always the anode side and the short side is always the cathode side, because of ACE, from the anode to the cathode to the electrolyte. Okay. With the cell, the most basic type of cell that we have, I want you to take a look at this diagram here, and I'm going to go through it with you. First of all, do we have the basic parts? We have the anode, we have the cathode, we have the electrolyte. So our ACE is in place. Now, the reason why the electrons are flowing in this way is because of the battery. So take a look again. Long to short, join them together, and you can see straight away that there's an arrow going this way, which means that the electrons are going to flow from this end and then back into this end here. Now again, another, if you want to get a little bit more technical about it, which as chemists we don't really need to, but if you're a physicist you'd say, oh yeah, well the reason why the electrons are coming from here is because they are being repelled by the negative charge present in the battery, and the reason why the electrons are going here is because they're being attracted by the positive end of the battery. Okay, look, just keep it easy. Take the arrow I showed you, make the arrow, and then realize the electrons flow out of the short end and back towards the long end. Okay, now when they do that, what happens? Well, they come, the journey starts here. So they come from the anode up through the wire into the base of this battery. So they go in there. Then electrons flow from the negative terminal through the wire again and down into the cathode, where they gather. Now the electrons will build up down here, so therefore these electrons are now available for species in the electrolyte to come and take them in order to bring about a chemical reaction. And likewise here, for the anode to be able to give electrons up to the battery, something else in the electrolyte must arrive at the anode and surrender. Okay, so the anode side is where substances surrender their electrons. The cathode side is where substances pick up electrons, and hence the reason why there will always be a chemical reaction at the anode and a chemical reaction at the cathode. Now you might be wondering, what's this thing here? That's what we call an ammeter. What does an ammeter, if you remember from your junior cert science? An ammeter simply shows me the presence of a flow of electrons. The larger the reading, the faster the flow. Okay, so the ammeter is evidence of a flow of electrons. And we just put that in there in order to show that the electrons are flowing. And if the electrons are flowing, then chemistry is happening down here at the anode and the cathode. Remember, ACE, from the anode to the cathode and then into the electrolyte where the chemistry happens. Okay, so the first one, which we would normally do in the classroom, is the electrolysis of potassium iodide solution. Now, I want you to think very carefully about what I've said there. Potassium iodide solution, which means if you're taking something which is highly ionic, as Ki will be from the positions on the periodic table, K is in group 1, I is in group 7, you can't have them further apart, so therefore their chemistry will be extremely ionic. When you put them into water, they will become K plus and I minus. Okay, now also in there you have a solution of Ki, so there's water in here also. So there are three things in your electrolyte. There's potassium ions, there's iodide ions, and then there are the water molecules that keep the iodide ions and the potassium ions in solution. So what we notice is this. First of all, K plus is extremely happy to remain K plus, because K plus is potassium which has lost an electron. And if you look at your periodic table, potassium that has lost an electron has noble gas configuration. Iodine also, having gained an electron, has electronic configuration of the nearest noble gas. But because of their reactivities, potassium is far more stable than iodide. So in this case here, we've got the iodide ions having their electrons delivered at the anode. See that? So these species here, the I minuses, will move over towards the positive anode. They will surrender their electrons, and then their electrons, because of this supply up here, remember again, do that, join them together. So the electrons then, when they're surrendered at the anode, will be taken to the battery. Electrons will be pumped from this end down here, so the electrons will build up on this. Now, K plus is stable, very stable, and therefore forget about it. It ain't going to react. I minus is also stable. However, because of its position on the periodic table, it's quite an easy element to get to react. So the two things that will react are the I minus, which will go to the positive anode, deliver their electrons, and the only thing then that's left to react at the cathode is water. So what we would notice here is that all of a sudden we would see that reddish brown colour of iodine, because what will happen is the I minus will surrender an electron, then another I minus will surrender an electron, and the two I's will form the normal elemental I2. Okay, if we take a look at that, there it is. So two iodines will surrender two electrons at the anode, and then those two iodines will join together as I2. So two iodides lose two electrons and become iodine. So you'll notice down here the reddish colour of iodine, yellowy kind of brownish colour of iodine beginning to form at the anode. Over here, what will happen is that the water molecules, they will go over to the cathode where they will pick up the two electrons. Now, what I need to say here is this. The number of electrons that are surrendered at the anode should always be balanced with the number of electrons that are taken at the cathode. Okay, so two iodides surrender two electrons and become I2. Those two electrons then are picked up from the cathode side by two water molecules. And when the two water molecules pick up two electrons, they will break up into hydrogen gas and OH minus. Now, if I was to put in phenolphthalein, remember what phenolphthalein is? It's the indicator we use to demonstrate the presence of a base. Okay, and it turns pink in a base. Notice what it says down here. When phenolphthalein indicator is added, the solution around the cathode begins to turn pink. And the reason for that is because as your hydrogen gas is being formed and bubbles like that, we also get an excess of OH minuses being formed, which means all of a sudden the pH around the cathode starts to drop. And when the pH starts to drop, then the phenolphthalein begins to turn pink. So phenolphthalein will turn pink over here, and on this side you'll have that lovely reddish, brownish, yellowy colour of free iodine being formed from every 2 iodide ions that surrender their electrons. Okay. Now, you may have looked at this in your junior cert, but this is what we call the electrolysis of acidified water. And with acidified water, you might ask yourself, why does it have to be acidified? A couple of drops of H2SO4 have to be added to the water in order to make sure that there are ions present in the electrolyte. So we do add in a few drops of concentrated H2SO4 just to make sure that there are ions present in the electrolyte. Once the ions are present, the electrolysis can happen. So what have we got in this setup here? We have water in this most unusual setup, which, if you haven't met it before, is called a Hoffman voltameter. Okay, and Hoffman, the way we were always told to remember it in school, it's like a H, see it? H with a little bar across. So it's a Hoffman voltameter, and the Hoffman voltameter is used in order to electrolyze water, bringing about chemical reactions at either side. So have we got the situation here of a cell? We have the electron pump, that's your battery, so that's your electron pump. Okay, what does that do? Well, keep in mind that the negative terminal is the one that delivers the electrons. The positive terminal is the one that takes in. So this is like an electron sponge. It takes in electrons this way, whereas the negative terminal pushes them out. So the cathode will always have electrons on its surface that are ready to be given away, whereas the anode will be taking in electrons continuously. And the number of electrons that are taken in at the anode and the number of electrons that are given out at the cathode, they should be the same when you're writing your equations. Now, in this case, we notice that the only thing we have present here is water. There is absolutely nothing else in the water except a few drops of H2SO4, which, as we said already, are used just to put ions into the water so that the water or the solution itself can act as an electrolyte. So let's take a look and see what happens at the cathode. At the cathode, we have 2 H pluses picking up 2 electrons in order to become hydrogen gas. Now, hydrogen gas, because it's a gas, it will always bubble upwards. So sometimes you might see an arrow like that, which just basically means that you've got bubbles and the gas is being collected up by downward displacement of water, as you can see here. So as the gas collects here, the water is pushed downwards. But you might say, where's the 2H plus coming from? Do you remember when we studied water in a previous chapter, we said that water itself does self-ionize. It does become H plus and OH minus, although to a very, very tiny degree. However, there are H plus ions and OH minus ions in water. So therefore, the H plus itself will obviously be attracted to the cathode because the cathode is negative, and the OH minus will be attracted to the anode. So now we know that the H plus comes over here, it picks up 2 electrons at the cathode, and it becomes hydrogen gas. So all the electrons are just, they're like on the surface like that, see that? They're there. So these 2 H pluses, they pick up 2 electrons and they become hydrogen gas, which bubbles. On the other side, you have 2 OHs coming over, and they will surrender 2 electrons. So the OH minuses, 2 of those, will surrender 2 electrons over here, which will immediately be taken in and given to the battery, and the reconstitution of the 2 OH minuses will form 1 water molecule and a half of a molecule of O2. Now, I all know you're very good chemists, and I know you're shouting at me, there's no such thing as a half a molecule of O2. But the reason why I have to leave it like that is to keep the number of electrons balanced. But there's another reason, and I don't know whether you can see it or not. Hydrogen has a coefficient of 1, oxygen has a coefficient of a half. Now look at the arms of your Hoffman. There will always be twice the amount of hydrogen to oxygen because the molecule itself has twice the amount of hydrogen to oxygen. So even the electrolysis agrees with the constitution of the H2O molecule. Okay, so it's quite a clever bit of chemistry. So just to go through it again very quickly, you have concentrated H2SO4, a couple of drops added in to provide the ions to ensure that this solution acts as an electrolyte. Water self-ionizes to a very tiny degree, but because and thanks to the acid being there as well, we'll have a decent concentration of H plus and also a concentration of OH minus. The H plus will be attracted to the negative cathode. The negative cathode has free electrons on its surface, so the H plus comes over here, picks up electrons, and the minimum number of electrons it picks up is 2. Because don't forget, elemental hydrogen is H2. So therefore 2 H pluses pick up 2 electrons and become elemental hydrogen. Okay. On the other side, 2 OH minuses surrender 2 electrons. You can see the electrons up there. They surrender 2 electrons and they reconstitute themselves into 1 molecule of water and half a molecule of oxygen gas. And again, you may sometimes see that little arrow like that, telling you that the oxygen gas itself is being bubbled. The lovely thing about it is it's 1 H2 to a half an oxygen. 1 to a half, not a proper ratio, better known as 2 is to 1. So there'll always be twice the amount of hydrogen to oxygen in a Hofmann voltmeter. Okay. Sodium sulfate is a very interesting solution because again, if you think about what we have, we've got sodium sulfate solution, which means that when you put Na2SO4 into water, you will have water. And you will also have this being ionic, because don't forget, you have sodium, which has a charge of +1. You've got the sulfate radical with a charge of -2. So you need 2 +1s in order to link perfectly with 2 minuses. Okay, so that's why it's Na2SO4. But as soon as you put that into water, they detach, they dissociate, and you get 2 Na pluses, and then you get your SO4 2- radical, your sulfate radical. Now, the one thing I hope you remember is, again, from potassium in the previous slide, sodium that has lost an electron has noble gas electronic configuration, stable, and it's very, very stable, so therefore it's not available to react. Okay, the sulfate radical itself, if you remember when we were doing our anions, is itself a very, very stable radical. Remember the hard water? It's the sulfates that give permanent hardness, so therefore the sulfates are also extremely stable and they're not available to react. So you might say to yourself, well, what is available to react? The only thing left available to react is water. So that means that water molecules will go to the anode where they will surrender electrons. The other water molecules will come over here to the cathode where they will pick up electrons. Now, again, remember we said water is amphoteric. Water can act as an acid or a base, and that's the reason why water molecules can both surrender and also accept electrons. So one water molecule over to the anode where it surrenders electrons and reconstitutes itself, and then H2O comes over to the cathode, gains electrons and reconstitutes itself. Now you might ask yourself, how is that the case? What way does it work? Well, if we take a look over here, 2 water molecules, when they reach the anode, will surrender 4 electrons. And when they surrender 4 electrons, the 2H2O becomes 4 H's and O2 gas. So again, you'll notice bubbles of oxygen here on this side. On the other side, again, you have 2 water molecules, and this time they pick up 2 electrons. So they pick up an electron each, and they reconstitute themselves into hydrogen gas and 2 OH minus hydroxyl radicals. Okay, now here's what I want to show you. First of all, the green color here is universal indicator. So it's universal indicator. Now, the universal indicator, when it's neutral, is green. But notice what's happening around the anode and around the cathode. It's beginning to change from green to red, which means there are acidic properties over here around the anode, and then around the cathode it's beginning to turn purple, which means we're beginning to see basic properties of the solution around the cathode. Now, why is that the case? Well, let's go through it again. You've got water molecules arriving at the anode. 2 of them will surrender 4 electrons and reconstitute themselves into oxygen gas, which bubbles away. But look, an excess of 4 H pluses are left behind, and that is what's responsible for the acid causing the universal indicator to turn red. It's a build-up of H plus ions around the anode. Here, at the cathode, we have two water molecules taking in 2 electrons, absorbing 2 electrons. They reconstitute themselves into hydrogen gas, which again will bubble away, but they leave an excess of 2 OH minuses, 2 hydroxyl ions. And the hydroxyl ions, as we know, are responsible for basic characteristics. So therefore here we get the pH rising above 7. Or in this case, the universal indicator going from green to purple. So that's the reason why when we electrolyze sodium sulfate solution, the sodium, nothing, the sulfate, nothing because of their stability. So it's water molecules on either side that will come to the anode and the cathode. At the anode, they will surrender 4 electrons to form oxygen gas and H plus ions. At the cathode, they will pick up 2 electrons in order to form basic OH minus ions and hydrogen gas. But I want you to just notice one more thing. The H2H2Os over at the anode, they surrender 4 electrons. Here, the 2 H2Os, they only take on board 2. The electrons aren't balanced. So if I was to balance this, I would have to multiply everything here by 2, which would give me 4 of them, 2 of them, and 4 of them. Now look, 2H2 to O2, the same ratio. 2H2 to 1O2, still a ratio of 2:1 between the hydrogen and the oxygen. So again, a lovely verification as to the structure of the water molecule. Okay, now just take a look at this one. These electrodes here are both made of the same metal. They're both copper. But you notice that there's copper somewhere else? There's copper in the electrolyte, copper ions, Cu2 pluses. And again up here, we have our power supply. Now again, let's just do this. Join those two, and now we know exactly how the flow of electrons is going to take place. So the flow of electrons goes from A to C to E, from the anode to the cathode to the electrolyte. Okay, so the anode is where the electrons are going to go up from. They will then move from there down to the cathode, which means that the anode will become positively charged, the cathode will become negatively charged, and that's thanks to the battery, because the battery always dictates what way the electrons are going to flow. Now if that's the case, now let's take a look in here. What have we got? We've got CuSO4 electrolyte, which when you put CuSO4 into water, you'll get Cu2 plus and SO4 2 minus. So you'll get a copper ion and a sulfate radical, which doesn't react because it's extremely stable. So that means that you've got Cu2 plus in here in the electrolyte, which is only waiting to pick up 2 electrons in order to go back to being copper metal. Where will they pick up those electrons? Over here. The electrons will be on the surface of the copper. So when the Cu2 plus comes over here, it'll pick up 2 electrons and become copper metal. What happens on the anode side is that the copper is stripped of 2 electrons. So copper metal loses 2 electrons here and becomes copper ions. And the copper ions can no longer remain part of the elemental copper, so they fall off into the electrolyte. Then they travel over here to the cathode, where they pick up 2 electrons again and become copper metal. So you see what's happening? You've got copper metal here becoming copper ions because 2 electrons have been taken away by the anode up towards the battery. You have the copper ions then going over to the cathode to reclaim 2 electrons to become copper metal. So therefore, over time, what we would notice here is that the anode would actually begin to wear away. And you'd notice the impurities, if there were any impurities present, the impurities would begin to build up down here. Whereas pure copper metal would begin to stick to the outside of this cathode, increasing its mass. Now the lovely thing to say here is, if you were to run this for a half an hour, this would more or less wear away. This would become very, very big in size, but the total mass of the entire system would remain exactly the same. So what in essence you're doing is you're transferring copper from this anode through the electrolyte over to the cathode, where it becomes copper metal again. So copper loses 2 electrons, that's its valency, and then becomes copper ions, which goes into solution, travels to the cathode, picks up 2 electrons and becomes copper metal. And this system is used as a way of purification of metals. So in other words, if you had impure copper, this one here could be impure, which means that as the electrons are taken away up here, the copper goes into solution and the impurities fall off down here. So all these impurities then can be collected and dumped, whereas the copper itself is transferred into solution, travels to the cathode, picks up 2 electrons and becomes pure copper metal. So this is where the pure copper metal will be, and this is where the impure copper metal will be, so you can remove the impurities by electrolysis. Okay, so over time, the anode loses copper and wears away, whereas on the other side there, just let me get rid of my annotations. On the other side, the cathode will gain copper metal and it gets thicker. All right, so just keep in mind, it's a lovely way of purifying an impure bar of copper into pure elemental copper. Now, ions in an electric field. I think this makes perfect sense. In an electric field, there is a positive charge and a negative charge. Ions are positive and negative, depending on which side of the periodic table you're going to be on. So therefore, if you have positive and negative ions all mixed together, and you put in a negative and a positive electrode, obviously the negative ions are going to be attracted to the positive electrode, whereas the positive ions are going to be attracted to the negative electrode. In other words, the positive ions are attracted to the cathode, which is negative, and the negative ions are attracted to the anode. And now you've got 2 words that we came across before, an anion and a cation. And I had mentioned these before, particularly when we were doing the anion tests at the very beginning of 5th year. And I told you, don't worry about the name, we deal with it when we're doing electrochemistry. An anion is an ion that is attracted to the anode. Now, if the anode is positive, then the cation has to be negative. A cation is an ion that is attracted to the cathode, meaning if the cathode is negative, this ion must be positive. See that? So that's what an anion and a cation are. An anion is an ion attracted to the anode. And because the anode is positive, the ion therefore must be negative. So all anions are negative in nature. A cation is an ion that is attracted to the cathode, which means that it's attracted to the negative electrode, meaning the ion itself must be positive. So therefore all cations are positive. So anions are negative in nature and cations are positive in nature. Okay, just to get that out of the way. Now, just a lovely example that they have in the book, and I have a video of this thing down here that you can have a look at later on yourselves. But if we were to take a mixture, okay, of blue copper ions and yellow, what we would call chromate ions. If we were to mix those together, blue and yellow makes green, okay? So we'd end up with a kind of a green solution. Now, notice that the copper is positive and the chromate is negative. So all I'm going to do here is I'm going to take that mixture of the blue and the yellow ions and put them into the middle. So that's a kind of a very, very concentrated green, dark green band. And in that dark green band, you have a concentrated mix of copper ions and chromate ions. And then what I do is I have the positive and negative terminals. So there's your cathode. It's your cathode because it's negative. So that's your cathode. And there's your anode. And I have the electrolyte split between 2 Petri dishes. Now, because the electrode is joined by a bit of filter paper, the whole thing acts as a simple cell and a single cell. So don't worry about that. That's a bridge. Okay, we sometimes call these a bridge. But it's a bridge that basically allows things to flow from one side to the other. So as far as this is concerned, it's a single unit. What happens when I turn on the power? When this becomes negative and this becomes positive? Well, think. The Cu2+, which is blue, will move towards the cathode. So you should have a movement of copper here, 2+, which means you should begin to see the blue coming out over here. And then the yellow, CrO4 2-, should start to move, CrO4 2-, should start to move towards the positive end, which means I should see yellow over here. And after I switch it on, watch, because I have a picture of this, that's exactly what happens. The blue moves, as we said already, towards the cathode, and the yellow moves towards the anode, and we can actually separate the two ions based on their charges alone. Now there is a video of it. Take a click on that yourselves. The video's down there. You can press on that yourselves when you're going through the slides. Have a look at the video of the process and just see the colours move away from one another. It's a very speeded up process on the video because it takes quite a long time. These are ions moving through filter paper, so they have to speed it up in order to show you the process in a time that is easy to watch. Okay, so electroplating. I think you might have mentioned this in junior cert. Electroplating is nothing more than plating a cheap base metal. So like what? Like nickel, for example, with a much more precious metal like silver. So you could have nickel and you might cover in silver, which therefore gives you what's called electroplated nickel silver. And you might see that sometimes, electroplated nickel silver. Take a look at your mother's and father's good cutlery. Take out the box and have a look and see, are those 4 letters printed on it? Because if they are, then you've only got a layer of silver over a base metal of nickel. Not really worth much. But if it's stamped with the hallmark of silver, then there's an heirloom there. So make sure you get to your parents and tell them, leave that to me, because that's pure silver. But if EPNS is on it, it basically means that you've got a base metal like nickel over which is a layer or 2 of solid silver. Doesn't really increase the value, but it makes it more resistant to, I suppose, corrosion and less corrosion and more tarnishing that we don't want to happen. So EPNS is electroplated nickel silver, where a cheap base metal like nickel is plated with silver. So how do I do that? And the answer is through electrochemistry, through electroplating. And again, let's just take a look at the setup. We have an anode, we have a cathode, and we have an electrolyte. Now in this case here, you'll notice that the spoon is going to be a nickel spoon, okay? Nickel spoon, so a cheap metal. And that forms part of the cathode. Over here, we have a bar of pure silver. And in the electrolyte, we have silver ions. So, what happens when I switch on the power? First of all, ACE, ACE. The arrow points this way, which means the electrons are going to move up away from this bar of silver, making that the anode. They will then reach this terminal of the battery. Electrons then will come from this end down and they'll gather over the surface of the spoon, like that. So all the electrons will gather on the surface of the spoon, making the spoon negatively charged. So now, because the spoon becomes negatively charged, the silver ions, which are positive, can flow across to the spoon, pick up the electron they require, become elemental silver, and when they do that, they stick to the surface and they begin to plate the surface of this nickel with the beautiful silver shiny metal we all know and love. Okay, so that's a very simple chemistry. So ACE, what happens here? ACE, well, here silver, what does it do? Sends electrons to the cathode, which is your spoon, nickel. And what happens then? The Ag pluses pick up an electron and become Ag metal. And that Ag metal, silver metal, sticks to the surface of the spoon and coats the spoon with a lovely layer. The longer you leave it, by the way, the heavier the layer will get, or the thicker the layer will get, increasing the value and also increasing the ability of the spoon to withstand tarnishing and corrosion. Okay, so let me just take off my annotations. So the spoon is being plated with silver, and 2 conditions must be met. First of all, the anode itself must be made of the same metal that you want to coat the spoon with, i.e. pure silver. And the electrolyte must also contain the ions of the metal that you want to plate with. So the only thing that's not allowed to be silver is the object that you're going to plate. Okay, so the spoon is nickel, the anode is silver, and there are silver ions inside in your electrolyte. That's how the flow of silver from the anode into the electrolyte and over here to the spoon, that's how it's effected. Okay, so at the anode, silver, which is in the metal here, loses an electron, E minus, so it loses an electron and becomes Ag plus. Now when it becomes Ag plus, it falls off, can't be any part of the elemental bar anymore, so it falls into solution, travels across, the Ag plus picks up its electron and becomes Ag metal, and that's what sticks to the spoon. Okay, so Ag, the silver, loses an electron to who? To the battery. The electrons travel up this way here. Up they go towards the battery. See that? And in there. All right. And what happens? They lose 1 electron each, forming the Ag+, which then goes into solution. So the Ag pluses here will go into solution. On the other side, the Ag plus goes over, picks up an electron, and becomes silver metal. Now, we're nearly done because the activity series is the last slide in this particular batch, and you may, depending on your level of chemistry at junior cert, you may have heard of the activity series. But the activity series is a list of metals which obviously are arranged in decreasing order of activity. Okay, now this is something I'm going to ask you to learn. So I'm going to finish this lecture here. I'm going to leave you with the activity series, which you folks are going to learn. And the activity series is nothing more than potassium, sodium, calcium, magnesium, aluminum, zinc, iron, lead, hydrogen, copper, mercury, silver, and gold. Do you notice anything? It's the activity series of metals. I'll go through it again. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead. No problem. All metal. Hydrogen? Oh dear. Hydrogen is a gas. Underneath that, copper, mercury, silver, and gold. Why is hydrogen in there? Why is hydrogen part of the activity series? The reason is simple. The metals that are listed above hydrogen have the ability to displace hydrogen gas from acids. So in other words, if your little aluminium ring falls into a bath or a vat of vinegar, tough. It's going to react with it. It's going to kick out hydrogen of the acid and form an aluminium salt. Okay. In fact, if any of these metals up here fall into acid, they will react by displacing the hydrogen out of the acid and forming a salt. What happens if your lovely gold ring falls into a vat of acid? Nothing. It'll sink to the bottom. You put your hand in, you take it out, and then your flesh is gone. No, you don't. You leave it. You fish it out some other way. But gold, silver, mercury, and copper are very, very resistant to reacting with acids. So silver, mercury, copper, and gold, they're the four metals that were at the very bottom of this activity series. Okay, and the reason, as I told you, hydrogen is there, is it separates the activity series into metals that can displace hydrogen and those that cannot displace hydrogen from acids. In other words, they don't react with it. And that's the reason why silver and gold have been metals that we have continuously modelled and fashioned into jewellery, and we've gathered because we know that they're special metals. Okay, now how do I remember this? And you're going to learn it. There's a rhyme, and we learned this rhyme when we were in school. Poor spelling can mean absolute zero in leaving honours, chemistry, math, science and geography. Now you're going to go to bed saying that tonight. Poor spelling can mean absolute zero in leaving honours, chemistry, math, science and geography, and you're going to say it to yourself 1,000,000 times, so that when you wake up in the morning you're going to hear yourself saying poor spelling can mean absolute zero in leaving honours, chemistry, math, science and geography. Now why would you say that? Because the first letter of each of those words happens to be the first letter of the metals in that particular order. So poor spelling can mean potassium, sodium, calcium, magnesium. Absolute zero in leaving. Aluminium, zinc, iron, lead. Honours, hydrogen. Chemistry, math, science and geography, copper, mercury, silver and gold. So please learn the activity series. It is a series of metals that are listed in order of decreasing activity. So that means potassium would be the most active, whereas gold would be the least active. And another way to say that, potassium would be the most reactive, gold would be the least reactive. You know what happens when we put potassium into water? Yeah, we get that flame and we get that pop. Okay, when we put gold into water, nothing. When we put gold into acid, nothing. So therefore what's happening is their reactivity is decreasing as we move from potassium down to gold. I'm going to pause there. I'm going to leave you with that. Okay, there's quite an amount in there. You're going to have to go over this lecture a couple of times just in order to make sure that you understand the processes involved in the different electrochemical processes. If you have questions or if there's anything you need me to further clarify, send me an email and I'll clarify it for you.